Hello everyone, and welcome back to the final video lecture for the Calculus 1 video lecture series, in which we're going to cover one last basic integration technique called U-Substitution. So just as a reminder with integrals, there is no product rule for integrals, there is no quotient rule for integrals. There's not really a chain rule for integrals either. So products, quotients, and compositions do need to be handled on a case-by-case basis. There are various techniques that work great for certain types of products, quotients, and compositions, and some that don't. So unlike derivatives where you had solid rules for each of these, for integrals, it's really on a case-by-case basis. You're going to cover a lot more integration techniques in Calculus 2, which is going to be the focus of pretty much the first half of the course. We're going to do one basic integration technique in this course called U-Substitution, which works really great for some types of functions. So some techniques are going to work sometimes, some not always, and there are some functions that are just non-integrable. You're going to see those in Calculus 2 and beyond. So here's how the substitution rule works. So it's for very specific types of integrals. So if the integral itself contains a composition, f of g of x, where f is the outside function and g is the inside function, and it is multiplied by the derivative of the inside function, so g prime, you're going to let some dummy variable u equal the inside function g of x. And after a whole lot of differentiating and substituting, it will substitute down into the integral of f of u du. Remember that whatever variable your function is in terms of needs to be the exact same as the variable of integration. So if you were integrating f of x, it needs to be integrated with respect to x, so dx. If your variable is u, it needs to be integrated with respect to u, so du. So I think the easiest way to demonstrate how this works is just to show you an example, but here is in words the substitution rule. So what you're going to do is you are going to find the composition f of g of x, and you are going to let u, some dummy variable u, equal the inside function g of x. Then you're going to take the derivative of u, which is du, and that will equal to g prime. Then you are going to substitute u in for g of x in the original integral, and you're going to substitute g prime in for du in, you're going to separate du in for g prime in the original integral. Then you're going to evaluate the new indefinite integral with respect to your new variable u. It has changed the variables. And then don't forget, if the original variable was x and the original integral was in terms of x, you need to end in terms of x, so just substitute g of x back in for u. Now, keep in mind, this is for extremely specific types of integrals, so obviously not all integrals are going to yield to the substitution rule. But when they do, you're going to find that they're actually really easy to work with. So we are going to use U-substitution on this integral here. Now, the only way to avoid U-substitution would be to expand this out 3 times, which is doable, but we're going to see how U-substitution works. So with U-substitution, you need to find the composition, and the composition is right here, this 2x plus 1 to the third. The outside function is the third, and the inside function is 2x plus 1. So we're going to let some dummy variable u equal the inside function, 2x plus 1. Then we are going to take the derivative of u with respect to x. So the derivative of u with respect to x, and yes, you do need to use Leibniz's notation, is going to be 2. Now, if you remember, you can multiply both sides by dx, and that gives you du is equal to 2dx. So here's what we're going to do. We're going to be doing a whole lot of substituting. You are going to be substituting u in for g of x, du in for g prime x d of x, and you are going to be actually integrating the outside function f with respect to your new variable u. So in my original integral, I am going to substitute u in for that inside function. Both the 2 and the dx, well, 2 dx is equal to du, so both the 2 and the dx are going to be substituted with du. And that outside function, that third power, is what we are going to be integrating. So when you do all the substitution, it will look something like this. That will get replaced with u. We're going to raise it to the outside power 3. And then 2 dx all got replaced with du. So the variable that we're integrating, u, is the same as the variable we're integrating with respect to, du. So since all of the variables match, now we're going to find the general antiderivative of u to the third with respect to u. So we're going to use power rule. We're going to increase the power by 1, divide by the new power. Since this is a definite integral, we do need a plus c. However, if you started this integral in terms of x, you need to end in terms of x. So since u is equal to 2x plus 1, what you're going to do is you're going to substitute 2x plus 1 with parentheses around it back in for u. So that will give you 2x plus 1 to the fourth over 4 plus c. And then that is going to be your final integral. So this next one is going to be very similar. If you want to try this before I go over it, just pause the video right now and then resume it when you are done working. But for U-substitution, what you're going to look for is look for the composition. The composition is here this e to the power of 10x, where e is the outside function and 10x is the inside function. So since 10x is the inside function, I'm going to let some dummy variable u equal my inside function 10x. Then I'm going to take the derivative of u, so the derivative of 10x is 10, and we're just going to go ahead and move the dx over to this side right now, because we're going to have to do it anyway. So du is equal to 10 dx. So as far as what gets substituted, this 10x we are substituting with u. Both the 10 and the dx are both getting substituted with du. And remember, we are going to actually integrate the outside function, so we're going to actually be integrating this exponential base e. So when we do all the substituting, we get the integral of our outside function e to the power of the inside function, which I'm substituting for u, and then 10 and the dx both got substituted for du. So since all of my variables are the same and they have all been changed, the integral of e to the u with respect to u is e to the u plus c. However, just remember that if you start in terms of x, you need to end in terms of x. So I'm just going to take 10x and I'm going to substitute it back in for u, giving you e to the power of 10x plus c, and then that is going to be your final answer. Now for this next one's going to be a little bit more difficult. So as soon as you see a composition, you should at least try to use U-substitution. The composition is right here, this e to the power of x cubed, where the exponential base e is the outside function and x cubed is the inside function. So I'm going to let u equal the inside function x cubed. Then after you figure out what you're supposed to let u equal, you're going to take its derivative. So du is equal to 3x squared dx. Power rule for derivatives. However, substitution is a delicate process. In order to substitute, what is here needs to be exactly equal to what is left over in your integral. So this 3x squared dx is not exactly equal to what's left over. What's left over is only the x squared dx. Unless it is exact, you can't substitute. So it is going to be an easy fix. To get rid of this 3, I'm going to divide by 3, or since division with integrals is really not a good idea, I'm going to instead multiply both sides by 1/3. So I get 1/3 du is equal to, those cancel out, x squared dx. Now that x squared dx, these are exact matches. Now we can substitute. So when you substitute, you're going to get the integral of, we're going to integrate this outside function e. That's what we're actually going to integrate. In place of x cubed, I'm going to substitute u. And then in for x squared dx, I'm going to be substituting 1/3 du. So times 1/3 du. And if you really don't like that constant multiple, remember, you can always take constant multiples out of the integral. So that's what I'm going to do. I'm going to put the 1/3 outside of the integral, and that'll be 1/3 times the integral of e to the u du. Now that all of my variables are the same and in terms of u, I'm going to integrate, so leave the 1/3 there. The integral of e to the u is itself. Since this is an indefinite integral, I need a plus c. And then just don't forget that if you start in terms of x, you need to end in terms of x. So I'm going to substitute x cubed back in for u. So I'll get 1/3 e to the power of x cubed plus c, and then that is going to be my final answer. Now for this next one, the only way to avoid U-substitution would be to expand this out 9 times, which I do not expect you to do and do not want you to do. Instead, I want you guys to think of this x to the 5th plus 6 to the 9th as a composition, where the outside function is that exponent of 9, the inside function is this x to the 5th plus 6. So I'm going to let my dummy variable u equal the inside function x to the 5th plus 6. So I'm going to take its derivative, so du is going to equal 5x to the 4th, and then just move the dx over to the right-hand side. Now remember, this outside power of 9 is what we're actually going to be integrating, so you're just going to leave that alone. X to the 5th plus 6, we're going to substitute that in for u, and x to the 4th dx needs to be substituted in terms of something du. However, remember, this needs to exactly equal what's left over. What's left over is just x to the 4th dx. But this is a 5x to the 4th dx, and unless this is an exact match, you cannot substitute. So the easy fix is just to get rid of this 5 by multiplying both sides by 1/5. So I've got 1/5 du is equal to x to the 4th dx. Now, x to the 4th dx, x to the 4th dx, it's exactly equal to what's left over, so now we can substitute x to the 4th dx with 1/5 du. So let's do all of my substituting. So I've got the integral of x to the 5th plus 6 got replaced with u. The outside power of 9 is what we're going to integrate. And then x to the 4th dx got replaced with 1/5 du. If you want to, you can take the 1/5 and write it outside of the integral. You don't have to, but you can do that. So we have 1/5 times the integral of u to the 9th du. So I'm just going to leave the 1/5 alone, and I'm going to use the power rule now that all of my variables have been changed and all of my variables match. So I'm going to increase the power by 1 and divide by the new power. Since this is an indefinite integral, you need a plus c. Then I'm just going to finish this up. 5 times 10 is 50. By replacing u with x to the 5th plus 6. Remember, if you start in terms of x, you need to end in terms of x. So I'm just going to replace u with x to the 5th plus 6 with parentheses around it, to the 10th plus c, and you do not need to simplify any further than that. I will say that the easiest way to master this is just to do a whole bunch of these. Also, for something like cosine cubed of x, you can leave it like this if you can recognize the composition, but remember, you can also rewrite that cosine cubed of x as the cosine of x parentheses cubed times the sine of x dx. I think if you write it this way, it might be a little easier to see what the composition is and what is the outside function and what is the inside function. So the cosine x cubed is obviously the composition. The outside function is that third power, and the inside function is that cosine. So since this is a composition, I'm going to try U-substitution. So u is going to equal the inside function cosine x. Then let's take its derivative. So the derivative of cosine is negative sine x dx. However, remember, this needs to be exactly equal to what's left over. Remember, we're going to integrate that outside function 3, so just leave it alone. That will get replaced with u. And sine of x dx, negative sine of x dx. It's an easy fix. I'm just going to multiply both sides by -1, so I get negative du equals sine of x dx. Now that this is exactly equal to what's left over, now we can substitute. So in place of cosine, I'm going to substitute u. Outside cubed is going to be what we integrate, and then sine x dx I'm going to replace with negative du. So I get the integral of u to the third times negative du. And if you want to, remember you can always take that constant multiple, that negative, and put it outside of the integral. So we'll get negative integral of u to the third du. So let's use power rule to integrate this. So I'm going to leave the negative alone. I'm going to increase the power by 1, divide by the new power. It's indefinite, so I need a plus c. And then just don't forget, if you start in terms of x, you need to end in terms of x. So we're going to write this as negative 1/4 times the cosine of x to the 4th power plus c. If you want to, you can also write this as negative 1/4 times the cosine to the 4th x plus c. It doesn't really matter. It's just nomenclature at this point, so whichever method you prefer to write this in. Now, for this next one, I highly encourage you, you can attempt it on your own if you want. I highly encourage you just to watch with this one because this one's going to be a little bit different. Now, as long as everything is in terms of the same variable, you can integrate. But if you have mixes of u's and x's, you cannot integrate. Everything needs to be in terms of the same variable. So either all x's or all u's. No mix and matching of the two. So for this next one, there is a composition. It is here in the denominator, where the outside function is that square root and the inside function is this x plus 1. So I'm going to let u equal the inside function, x plus 1. Then I'm going to take the derivative of u's with respect to x, so du is equal to 1 dx. So you might see where there is a problem. So in for x plus 1, we're going to substitute u. The outside function, that square root, is what we're actually going to integrate. Dx is getting replaced with du. However, that leaves this x in the numerator with nothing to substitute for. You cannot have a mix of u's and x's. So this x here in the numerator needs to get replaced with something in terms of u. And as long as it gets replaced with something in terms of u, you can substitute. So take a look on this page here. Is there anything, any sort of equation that relates u and x? It's right there. So if we were to actually solve this for x, if we were to subtract 1 from both sides, we would get x is equal to u minus 1. So that's exactly what I'm going to do with this x in the numerator. I'm going to substitute this x in the numerator with u minus 1. You can do that as long as everything is in terms of the same variable. So when I do my rewriting, in place of that x in the numerator, I replaced it with u minus 1. This inside function got replaced with u, and I'm just going to go ahead and rewrite that square root as a power of 1/2 right now, because I'm going to have to anyway. And then dx got replaced with du. So at least everything is in terms of the same variable. However, remember, there is no quotient rule for integrals. So when you see a quotient, you have to rewrite it so that you can get rid of the quotient and actually integrate. Now, since the denominator is just this one single term, u to the 1/2, what I'm going to do is I'm going to separate that subtraction in the numerator as a subtraction of two separate fractions with a common denominator. So I'm going to write this as u over u to the 1/2 minus 1 over u to the 1/2 du. And then I'm going to use my power rule for, I'm going to use my quotient rule for exponents to simplify this. So I'm going to subtract the exponents. 1 minus 1/2 is u to the 1/2. I'm going to rewrite this 1 over u to the 1/2 as u to the power of negative 1/2 du. So now that there are no more quotients, I don't have to worry about there not being a quotient rule. So what I'm going to do is now I'm going to use power rule to integrate all of this with respect to u. So for u to the 1/2, I'm going to increase the power by 1. 1/2 plus 1 is 3/2. Dividing by 3/2 is the same as multiplying by 2/3. Minus, I'm going to do the same thing here. So negative 1/2 plus 1 is u to the power of positive 1/2. Dividing by 1/2 is the same as multiplying by 2. And since this is an indefinite integral, we're going to add a plus c. And then just don't forget, if you start in terms of x, you need to end in terms of x. So I'm going to substitute x plus 1 with parentheses around it back in for each of these u's. So I'm going to get 2/3 times parentheses x plus 1 to the power of 3/2 minus 2 times x plus 1 to the power of 1/2 plus c. And then that is going to be my final answer. Now for this next one, there are some integrals that do not, that don't look like they have a composition at first glance, but they can actually yield to substitution rule. This is one of them. There's no composition that we can see here. But what we can do is we can let u equal to that denominator. That's really the only thing we have to choose from. And you're going to find that this integral, even though it doesn't involve a composition, can still yield to substitution rule. So I'm going to let u equal really the only thing we have here, which is the denominator x plus 6. So then I'm going to take the derivative du, which is going to be equal to 1 dx. So I'm going to replace this x plus 6 with u, this dx with du, and that's really it. We had nothing else to substitute. So we've got the integral of du over u. If it's not obvious and you don't like the way this is written, what you can also do is you can rewrite this as 1 over u du. Now remember, the only power that power rule for integrals does not work on is -1. Because you have to think to yourself, what function gives me a derivative of 1 over u? Well, that's actually natural log. So the natural log of the absolute value of u plus c is going to be our integral. And then remember, if you start in terms of x, you need to end in terms of x. So we have natural log of x minus 6 plus c. Technically, you do need the absolute values there in order to make sure that this x minus 6 stays positive and that this composition can even happen, because remember, you can't take the log of a negative. So basically, leave the absolute value bars there. You technically need them, so it's the natural log of the absolute value of x minus 6 plus c. So then for this next one, again, if you don't like the way the cosine squared of x is written in the denominator, you can change that to the cosine of x squared. And then I think if you write it that way, it might be a little bit easier to see what the composition is and what's the outside function and what's the inside function. So the composition is actually here in the denominator. The exponent, the squared, is going to be the outside function. The inside function is going to be the cosine. So I'm going to let u equal the inside function cosine x. So I'm going to take the derivative of u. The derivative of cosine is negative sine of x dx. Now, negative sine of x dx is not entirely exactly equal to what's left over, so I'm just going to fix that by multiplying both sides by -1. So I get negative du is equal to the sine of x dx. So let's do some substituting. In place of cosine, I'm going to substitute u. Remember, we're going to actually integrate that outside function, that power 2. So you're going to leave that alone. Remember, this is in a denominator, so even after substituting, it does need to stay in the denominator. And then in for sine of x dx, I'm going to replace that with negative du. So I'm going to get the integral of negative du all over u squared. And if you don't like the way this is written, you can do two things. You can take that negative and write it outside of the integral. You can move the du off to the side and put a 1 in the numerator. And then, because there is no quotient rule for integrals, you really do need to rewrite this 1 over u squared as some sort of u to a certain power that's not in a denominator. So I'm going to write this as u to the power of -2. So now that we've got this written in a form we can work with, now let's integrate. So I've got that negative that I pulled out front, I'm going to leave alone. I'm going to increase the power by 1. -2 plus 1 is going to give you -1. divide by the new power. This is an indefinite integral, so you need a plus c. So then we're going to, kind of clean this up a little bit. Negative divided by negative is a positive. And then if you start in terms of x, you need to end in terms of x. So I'm going to replace u with cosine x. So I have the cosine x to the power of -1. Negative divided by negative was a positive, plus c. And if you don't like the way this is written, if you don't want to get this mixed up with, cosine inverse, you can write this as 1 over cosine x plus c. And if you want to, 1 over cosine is also known as secant x plus c. However you want to write this, just don't get this mixed up with cosine inverse. And then that is going, either one of these is going to be your final answer. So then for these next two, for this next one, for this integral of natural log x over x, remember, there are some integrals that don't have a composition that can still use substitution rule. This is another one. So you have two options here. You have natural log and x. One of them is going to be the u, and remember, the derivative of u needs to be inside the integral somewhere. So if you've noticed, for every single one of these, the derivative of u was somewhere inside the integral. So let's let u equal the natural log of x, because if you let u equal the natural log of x, the derivative of the natural log of x is 1 over x dx, or you can write that as dx over x if you want to. Doesn't really matter. So as long as whatever you let u equal, as long as the derivative of u is in that integral somewhere, you can still use U-substitution. So I'm going to let u equal that natural log, and the 1 over x dx is going to get replaced with du. So when we substitute, we're going to get the integral of that got replaced with u, all of that got replaced with du. This is technically a u to the 1, so you can use power rule for this. So I'm going to increase the power by 1, divide by the new power, plus c. And then just don't forget to end in terms of the same variable, so I'm going to just plug natural log of x back in for u. So I've got natural log of x squared over 2 plus c, and that will be your final answer. Now for this next one, I think the composition is really obvious. The composition is here in the denominator. The cube root is going to be the outside function. Z squared plus 1 is going to be the inside function. So I'm going to let u equal the inside function z squared plus 1. So then I'm going to take the derivative with respect to z. So du is going to equal 2z dz. And then from here, the substitution is really pretty straightforward. So z squared plus 1 got replaced with u. We're going to actually integrate that cube root, so we're going to leave it alone. And then 2z dz is going to get replaced with du. So we will get the integral of du over the cube root of u. So let's just do a little bit of rewriting here so that we can actually integrate this, but everything is in terms of the same variable, so we're just about ready to integrate. So I'm going to do two things with that cube root of u. I'm going to rewrite the cube root as an exponent of 1/3, and I'm going to make it a negative 1/3 to get it out of the denominator. And then this is what I'm going to integrate. So I'm going to use power rule on this, so I'm going to increase the power by 1, so negative 1/3 plus 1 is u to the power of positive 2/3. Dividing by 2/3 is the same as multiplying by 3/2. This is an indefinite integral, so you need a plus c. And then don't forget, if you start in terms of z, you need to end in terms of z. So I'm just going to take the z squared plus 1 with parentheses around it and substitute it back in for u. So I have 3/2 times z squared plus 1 to the power of 2/3 plus c, and then that is going to be our final answer. Now for these next two, You can technically use U-substitution for these, because if you have anything other than just x inside your trig function, it technically is a composition. So if you're integrating cosine of 2x dx, you can use U-substitution for this. The inside function is 2x, the outside function is cosine. So if you let u equal the inside function 2x, you get du is equal to 2 dx. Because 2 dx is not exactly equal to what's left over, we're just going to multiply both sides by 1/2, so we get 1/2 du equals dx. So let's do some substituting. So in place of 2x, I'm going to substitute u. You're actually going to integrate the outside function, so leave the cosine alone. And then in place of dx, I'm going to substitute 1/2 du. So that is going to give me the integral of cosine of u times 1/2 du. You can take the 1/2 and write it outside of the integral if you want to. So we have 1/2 times the cosine times integral of cosine u du. So for the integral of cosine, what you are asking yourself is what function gives me a derivative of cosine, which is sine. So the integral of cosine is sine u plus c. And then just don't forget to substitute 2x back in for u. So we'll get 1/2 times the sine of 2x plus c. So I encourage you to try that for this next one. Pause the video right now if you want to try this one on your own. So the inside function is 3x. The outside function is sine. So I'm going to let u equal the inside function 3x. That means I'm going to take its derivative. Du is going to equal to 3 dx. 3 dx is not exactly equal to what's left over, so I'm just going to fix that by multiplying both sides by 1/3. So I have 1/3 du is equal to dx. So after some substituting, in place of 3x, I'm going to substitute that for u. The outside function sine is what we're actually going to integrate, so you're going to leave that alone. And then in place of dx, I'm going to substitute that with 1/3 du. So that will give me the integral of sine of, in place of 3x, I'm substituting u. I'm going to go ahead and pull out the 1/3 right now, du. So for the integral of sine, what you are asking yourself is what function gives me a derivative of positive sine? Well, that is negative cosine of u plus c. And then just don't forget to substitute 3x back in for u. So we've got negative 1/3 times the cosine of 3x plus c. So for this next one, you can use U-substitution if you don't want to expand this out 3 times. So the inside function is the 2x plus 1. The outside function is the 3. So I'm going to let u equal the inside function, 2x plus 1. So I'm going to take its derivative. Du is equal to 2 dx. 2 dx is not exactly equal to what's left over here, so I'm just going to multiply both sides by 1/2 to get 1/2 du equals dx. Which, now this dx is exactly equal to what's left over, dx. So in place of 2x plus 1, I'm going to substitute u. The outside function, that power 3, is what we're going to integrate, so you're going to leave it alone. And then in place of dx, I'm going to substitute 1/2 du. And then remember, you can always take that constant multiple out of the integral. So I'm going to take that 1/2 out of the integral right now, times the integral of u to the 3rd power du. So then I'm going to leave the 1/2 alone, and we're going to use the power rule. So I'm going to increase the power by 1, u to the 4th, divide by the new power, 4, plus c. So then I'm just going to clean this up. 2 times 4 is an 8 in the denominator. And then if you start in terms of x, you need to end in terms of x. So I'm just going to substitute 2x plus 1 with parentheses around it back in for u. And then this is going to be our final answer. So then for this next one, I see a composition there in the denominator. So since there's a composition, I'm going to try U-substitution. So the inside function is this 2 plus sine t. The outside function is that power 3. So I'm going to let u equal the inside function, 2 plus sine t. And then I'm going to take the derivative. So du is going to be equal to, derivative of 2 is 0. Derivative of sine t is cosine t dt. So then let's do some substituting. So if this 6 is getting in the way, you can always take it outside of the integral. So I'm just going to take that 6 and going to write it outside the integral and then do the rest of my substituting. So 2 plus sine t got replaced with u. It is in the denominator, so it does need to stay in the denominator. We're going to integrate that outside power 3. And then in place of cosine t dt, I'm going to substitute du. Since there is no quotient rule for integrals, I do need to rewrite that u cubed in the denominator as u to the power of -3 du. So we're just going to leave that 6 alone, and then we're going to use power rule on this. So -3 plus 1 is -2. And then we're going to divide by the new power, -2, plus c. And then just don't forget, we need to end in terms of the same variable t, so I'm just going to substitute 2 plus sine t with parentheses around it back in for u. So 6 divided by -2 is -3 times 2 plus sine t to the power of -2 plus c, and then that is going to be your answer. Now we've just done a whole ton of integrating using U-substitution with indefinite integrals. U-substitution can work for definite integrals as well, and you have a couple options for this. If you have a definite integral, your bounds are going to be in terms of x. They are bounds with x, not with u. So you have two options. You can either do some separate work off to the side and use the U-substitution to just get the general antiderivative and then back substitute x and then put it back in and then use your original bounds. So as long as you remember to back substitute, you can use your original bounds and there's nothing wrong with that. But if you don't want to back substitute, there is a way to change the bounds so that they are bounds in terms of u, not in terms of x, which would mean that you do not have to back substitute. So if you let u equal to the inside function g of x, then if you want to change the bounds, which remember, these original bounds a and b would be in terms of x, if you want to change them into bounds in terms of u, you're just going to plug a in for u, so that will give you g of a for your lower bound, and then plug b in for the upper bound, so your upper bound would be g of b times integral of from g of a to g of b of f of u du. If you change the bounds, you do not have to back substitute, and in fact, if you go to the trouble of changing the bounds, do not back substitute. So the bounds on a definite integral are always in terms of x to start, not in terms of u. So again, if you are in the habit of back substituting for x, then go ahead and do that. Use the U-substitution to just get the antiderivative without changing the bounds, and as long as you change back to x before evaluating the definite integral, you can use the original bounds. However, if you don't want to back substitute, just change the bounds. If you change the bounds, don't back substitute for x. So I'm going to take this next one and just show you how changing the bounds would work. So I'm going to just kind of proceed as normal. I'm going to find the inside function. The inside function is this x plus 3, so I'm going to let u equal the inside function, x plus 3. So then I'm going to take its derivative, so du will equal to 1 times dx. Now, the outside function 3 is what we're going to be integrating, so let's start with, what we're going to substitute inside the integral. So in place of x plus 3, I'm substituting u. The outside power 3 is what I'm going to integrate. And then in place of dx, I'm going to substitute du. However, let's also change the bounds. So let's start with that lower bound, x equals 0. And I'm going to change that lower bound into a bound in terms of u. So I'm just going to evaluate my u when x equals 0. So I'm going to plug 0 in for this x in u equals x plus 3. So u is going to equal 0 plus 3. So my new lower bound in terms of u will be 3. Then I'm going to do the same thing to change the upper bound. So I'm going to plug 2 in for this x in u equals x plus 3. So I have u equals 2 plus 3. So my new upper bound in terms of u will be 5. So this is what it will look like when we substitute. We're going to have on the bottom u to the power 3. Remember, if it's in the denominator, it needs to stay there. Dx got replaced with du. My lower bound 0 got replaced with 3. My upper bound 2 got replaced with 5. Then I'm just going to do a little bit of rewriting so that I can actually evaluate this indefinite integral. So I've got, u to the power of negative 3 du. And let's use a quick little bit of power rule. So I'm going to increase the power by 1. Negative 3 plus 1 is negative 2. And then I'm going to divide by that new power, negative 2. Since this is a definite integral and the c's are going to cancel out, I do not need a plus c. Now, because I went to the trouble of changing my bounds, I am not going to back substitute for x. So I do not have to plug x plus 3 back in for u. Because I changed the bounds, I can just go from here, from this u to the negative 2 over negative 2, and just evaluate this from 3 to 5. So I'm going to plug in the upper bound first. So I have 5 to the power of negative 2 divided by negative 2. Minus, now I'm going to plug in my lower bound. So I have 3 to the power of negative 2 over negative 2. And then when you evaluate this, you get 8 over 225. Which, you can leave it like that. Or I will also take 0.035, whichever. But this is going to be your final integral. So if you change the bounds, do not back substitute for x. You will not have to back substitute for x. Now for this next one, do not separate that plus sign in the denominator. The only fractions that you can separate are when the addition or subtraction is in the numerator, which it was a while ago. I must have skipped it. Hold on. Yeah, it was over here. So you can only separate addition or subtraction that is in the numerator as long as the denominator contains one single term. You can't do that here because the addition is in the denominator, so do not separate addition or subtraction in the denominator. So since there is no quotient rule for integrals, I'm going to try U-substitution. So I'm going to let u equal the denominator. No, there's no composition here. But remember, whatever you make u, the derivative of u needs to be in that integral somewhere. So the derivative of x squared plus 1 will involve x, which is in the integral. So I'm going to let u equal that denominator, x squared plus 1. And then I'm going to take its derivative, so du is equal to 2x dx. 2x dx is not exactly equal to what's left over here, so I'm going to multiply both sides by 1/2, so I'll get 1/2 du is equal to x dx, which is exactly what's left over. While I'm at it, I'm also going to go ahead and change my bounds to bounds in terms of u. So let's take the lower bound, and we're going to change it in terms of a bound in terms of u. So I'm going to plug 0 in for u equals x squared plus 1. So if u equals 0 squared plus 1, gives me a new lower bound of 1. Then let's take my upper bound 4 and do the same thing. So if u equals 4 squared plus 1, gives me a new upper bound of 17. So after we do all of the substituting, we're going to get the integral from our new lower bound 1 to our new upper bound 17 of all of this in the denominator got replaced with u, and then x dx got replaced with 1/2 du. If you want to, you can take the 1/2 out of the integral entirely to give you 1/2 times the integral from 1 to 17 of 1 over u du. Remember, power rule does not work on -1. What function gives you a derivative of 1 over u? That is a natural log. So we're going to have 1/2 times the natural log of u. And because this is a definite integral, I do not need a plus c. They're just going to cancel out anyway. And because I went to the trouble of changing my bounds, I do not need to put x squared plus 1 back in for u. I can just go from here and use my new bounds 1 and 17. So we're going to plug in the upper bound first. So we'll get 1/2 times the natural log of 17. Minus, now let's plug in the lower bound, 1/2 times the natural log of 1. Natural log of 1 is 0, so you're just going to do 1/2 times natural log of 17, which is 1.417. Approximately. I highly encourage you guys to try this one on your own, and I highly encourage you to change the bounds. Even though, technically you don't have to, for some problems, especially this one, changing the bounds actually does help. If you need a little bit of a hint, you can rewrite that sine to the fourth as, 1 over pi over 2. You can rewrite that sine to the fourth x as sine of x to the fourth times cosine of x dx. I think from here it might be easier to see what the composition is and what the inside function is. So go ahead and pause the video and try this one on your own. Okay, so the inside function is the sine of x and the outside function is that fourth power. So we're actually going to integrate that outside function, which means we're going to let u equal the inside function sine x. So the derivative of sine is going to be cosine, so du is going to equal cosine of x dx. And it's a pretty straightforward substitution. However, let's also change the bounds. So let's take x equals 0. We're going to plug 0 in for this x in our u function, so I have u is equal to the sine of 0. Sine of 0 is 0, so my new lower bound in terms of u is going to be 0. Now let's do the upper bound. So let's change the upper bound, pi over 2, into a bound in terms of u. So I'm going to plug pi over 2 in for this x in u, so I have u is equal to the sine of pi over 2. Sine of pi over 2 is 1, giving me a new upper bound of 1. So let's do all the substituting. In place of sine x, I'm going to replace that with u. I'm going to actually integrate the power of 4, so you're going to leave that alone. Cosine of x dx is getting replaced with du. My lower bound 0 is getting replaced with 0. My upper bound pi over 2 is getting replaced with 1. So I have the integral from 0 to 1 of u to the power of 4 du. Now that all of my variables match, the integral of u to the fourth, I'm going to use the power rule. So I'm going to increase the power by 1, divide by the new power. And I do not need a plus c since it's a bounded integral. And because I bothered to change the bounds, I do not have to back substitute. So I'm just going to use my new bounds 0 and 1. Let's start with the upper bound. So we'll have 1 to the 5th over 5. Minus, now let's plug in the lower bound, 0 to the 5th over 5. Which this is really easy to evaluate. You get 1/5. So changing the bounds for this one actually made this problem a lot easier. So that is it for U-Substitution, and that is actually it for Calculus 1. So this is going to wrap up the final section for your course. Thank you all so much for watching these video lectures. I had a lot of fun recording them, and thank you all so much for watching. I did put a lot of time and love into this, so thank you for watching, and I hope that these video lectures were valuable for you, and I hope that you all have a great end of your semester and you have a great summer. If you have any questions on this or any of the other video lectures, please don't hesitate to email me, and I will see you guys around. Bye-bye.